What is spontaneity? When we examine nature and take a close look at processes, the state they start from and the state they end at, we can see some pattern emerging. We can see that there's a natural tendency for some processes to occur spontaneously and for others not to. Let us consider a few examples of systems that you are familiar with. The first system is oxygen O2 gas, assumed to behave ideally. The second system consists of blocks of aluminum metal. The third system is a set of two gases, helium and neon. The fourth system consists of hydrogen and oxygen atoms. And the last system is a sample of water. While each of these systems can be imagined to exist in a limitless variety of states, to avoid making our argument unnecessarily complicated, we will consider for each system only two of their many possible states. For example, oxygen gas can be considered at a pressure P in a volume V, or at a pressure P divided by 2 in twice the volume. The two blocks of metal may be either at different temperatures, T1 and T2, or at the same temperature, Tf, intermediate between T1 and T2. The helium and neon gases may be either pure or mixed together. The hydrogen and oxygen atoms may exist in the form of molecular hydrogen and oxygen gases, or may be bound together in the form of water molecules in the liquid state. Finally, water may be in a liquid or solid states. Acknowledging the fact that a system can exist in two different states, let's say states A and state B, a number of questions come to mind. Does a system prefer to be in state A, in state B, or is it equally happy in either one of these two states? Another way to formulate the same question would be to ask, is the process that transforms the system from state A to state B spontaneous? Is the reverse process spontaneous? Or is there an equilibrium between states A and B of this system? From experience, we know the answer to these questions for the 5 systems described above. We know that upon opening the valve between the compartment containing the oxygen gas and the evacuated compartment, the gas will spontaneously expand to twice its volume and half its pressure under isothermal conditions. We also know that two blocks of metals at different temperatures will spontaneously exchange heat until they reach the same final temperature, intermediate between the starting temperatures. We also know there is a natural tendency for gases to mix, for molecular hydrogen and oxygen gases to react, thereby forming water, and for ice to melt under atmospheric pressure when the temperature is 70 degrees Fahrenheit. All these processes are spontaneous in the direction shown by the green arrow, and are non-spontaneous in the direction shown by the red arrow. However, you might say, wait a minute, I know we can transform water in the liquid state into oxygen and hydrogen gases through a process called electrolysis. We can compress a gas to half its volume and twice its pressure using special membranes and mechanical pumps. We can use special membranes and mechanical pumps to partially separate gas mixtures into their pure components. We can also use a refrigerating device, an electrical heater, to cool one end of a metal block while we heat the other end. So why are we saying that these processes are spontaneous in one direction and non-spontaneous in the opposite direction? Well, this must have to do with the thermodynamic definition of spontaneity. To illustrate the concept of spontaneity and develop some criterion that characterize spontaneous processes, To illustrate the concept of spontaneity and develop some criteria that characterize spontaneous processes, let us consider two states A and B of a gas contained in a cylinder and sealed from the surroundings by a piston of mass m. In state A, the pressure of the gas, P sub A, is larger than the external pressure, which consists of the atmospheric pressure and the pressure mg over A due to the weight of the piston. However, since the piston is locked in position by the presence of stops, the gas cannot expand and is at equilibrium. We can find another equilibrium state of the system, which we call state B, where the pressure P sub B of the gas in that state is equal to the external pressure. We can reach state B from state A by pulling the stops, which lock the position in place in state A. Since PA is greater than the external pressure, the gas expands spontaneously as soon as we pull the stops. The expansion is rapid and will continue as long as the pressure of the gas is greater than the external pressure. The new equilibrium state B is reached when the external pressure is equal to the pressure in the gas, P sub B. Obviously, needless to say that the reverse process is not spontaneous. Note that during the spontaneous expansion process, work was done by the gas on the surroundings. We will therefore state that a process is spontaneous if it occurs without the surroundings having to do work on the system. Obviously, what we have just said does not imply that the system cannot go from state B to state A. It can indeed do so non-spontaneously if work is done on the system by the surrounding, as is illustrated here through the action of placing an additional mass, m, on the piston. So this compression is a process that occurs non-spontaneously when mechanical work is done on the system. Similarly, the transformation of water molecules in a liquid state into oxygen and hydrogen gas can take place non-spontaneously when electrical work is done on the system during electrolysis. So we can state that non-spontaneous changes can occur when work is done by the surrounding on the system.